This is the symbol of inductance. Inductance is the physical property of a circuit that opposes any change in current. To simplify, the single wire connected to an AC supply. The flow of electrons in a wire creates a magnetic field all along the wire. We will see what happens at one point in this wire. What happens here happens at every other point. As the current builds up, lines of force cut through the wire, expand outward, and build a magnetic field. When current reaches maximum and drops off, the field collapses, again cutting through the wire, until both current and field pass through zero at the same instant. When the current reverses, the field again expands and collapses. This cutting of the wire by the field is the basis of inductance. To show better what happens, we substitute the field of a magnet, first with no current flowing in the wire. When any magnetic field cuts a wire, it will induce a voltage, which we represent by this symbol. This induced voltage tends to cause current to flow in the direction indicated by the arrow. If we reverse the direction of cutting, we reverse the polarity of the induced voltage. We apply a source of voltage represented by this symbol, and current flows in the wire. Now, one direction of the magnet's movement induces a voltage opposing the applied voltage. This reduces the total voltage acting in the circuit, and less current flows. Moving the magnet in the other direction induces a voltage aiding the applied voltage. This increases the total voltage acting in the circuit, and more current flows. The electromagnetic field of the wire does exactly the same thing. As the current builds up, the expanding field induces a voltage that opposes the buildup of current. At the instant current and field reach their maximum, the field is stationary. It is surrounding but not cutting the wire, so the induced voltage is zero. Now, as current and field drop off at an increasing rate, the induced voltage increases, opposing the decrease in current. When current and field pass through zero and change direction, the field is cutting the wire at maximum speed, and the induced voltage is maximum. This induced voltage that continually opposes any change in current is called the EMF of self-induction. When we bend the wire, the magnetic field cuts the wire at still another point. And since the field is at every point along the wire, the field at each point cuts other points. This multiplies the opposing effects of the induced EMF. As we add more turns to make a coil, the inductance increases, and the total effect of the field on all the turns greatly increases the opposing effects of the induced EMF. Adding a core of magnetic material also increases inductance by causing the lines of force to cut all the turns. When inductance is placed in an AC circuit, the polarity of the induced EMF is always opposite to that of the applied voltage. Therefore, it also opposes current flow. This opposition is called inductive reactance, or X sub L, and is expressed in ohms. In this circuit, when the inductance is large, the inductive reactance will be large, and little current can flow. If we decrease the inductance, we decrease the inductive reactance, and more current flows. If we increase the frequency, the speed at which the field cuts the turns increases. As a result, the inductive reactance also increases, and less current flows. We see that inductive reactance depends on two factors, inductance and frequency. The presence of inductance causes current to lag voltage. In a theoretical circuit containing no resistance, we will use meters to examine the time or phase relationship between current and voltage. When applied voltage reaches zero from the positive direction, current reaches maximum positive and has built a maximum field. As applied voltage rises toward maximum negative, current drops at an increasing rate. At the same time, the field is also collapsing at an increasing rate, and the induced EMF reaches maximum at the instant current and field pass through zero. Applied voltage drops to zero while current and field rise to maximum negative. Here the rate of change of the field is zero, resulting in zero induced EMF. We superimpose the meters and see that current lags voltage by 90 degrees.